Networking. Today we have a wonderful speaker. Azher Mughal is a network engineer at Caltech for the CMS Tier 2 data center. In the past, he worked for the US LH CNET and ultralight networks and was responsible for transporting LHC data from CERN to US labs. He is actively involved in designing high-performance systems, software-defined networks, and LHC PTP experiments involving provisionings, systems like OSCARS, NSI, and OESS. Please join me in welcoming Azher.
Thank you very much. It's a pleasure to be here this morning, and I'm listening to very exciting talks. My talk today is about the SDN activities and the software development that we have been doing in Caltech and for the CERN LHC at large. The talk mostly will, and the background is about how quickly one can move the traffic from point A to point B involving any of the experiments. So we'll talk about the LHC experiment in specific, but this applies to any experiment at large. So the Caltech CMS group has been involved along with various RNE networks and has been participating in the LHC1 and the point-to-point experiments. These point-to-point experiments leverage the facilities of different softwares provided by ESNet and Internet 2. Moving on, the NSF funding projects, DINES and ANSI, they took the initiative to design and deliver these applications for different experiments, and we have seen these running successfully in the past. Several large-scale demonstrations during the supercomputing in the past, starting from 2005, and as of last year, in 2015, we have seen that using the 10 gig connections and moving forward using the 100 gig connections, one can really, if they have the right set of tools and applications and services well tuned together, they can really reach to 1.5 terabit per second from a single booth. And if you see on the last one, the 2015, there we basically let the application handle the whole complete network, and we were able to design a software ring that was able to move around 0.5 terabit of data. The demonstration goals that we set for the SC15 conference, these were mainly the SDN traffic flow, the intelligent traffic flows, how you can steer the traffic across the whole ring. How can you, once you have the flows installed in an environment, then how you can steer them based on different intent. And we'll talk more on the intent-based methodology. Then the next one is the NSI WAN path. These are certain software aspects on how you can have heterogeneous network environment, and there you can control different WAN domains and then pull up a long paths together. Then designing the high-speed DTN servers ranging not just from 10 gig, 40 gig, but now talking about the 100 gig, because we have these network cards available and different switches, but whether we are really able to exploit those capabilities or not. So this is how we pulled everything together. In the center, you'll see SC15. There we had 9 100 gig connections altogether, with 200 gig connections going from our booth, while 2 other connections going from 2 other booths. So the participants, the key participants were the Caltech, Starlight, University of Michigan, Florida International University, campuses from Brazil, and the network providers from Brazil like RNP and the UNESP. The software that we used to provision this whole infrastructure on the WAN side were the OSCARS, OESS, NSI, and the OpenFlow in some of the parts. In order to carry on and do this demonstration at such a large scale at a convention center in a show, we really needed to have a fully and a versatile lab environment where we can have different kind of switches ranging from 1 gig, 10 gig, 40 gig, 100 gig, with different software pieces and different agents running on them, so that we know and we understand that when we take this software and do this all integration, then whether that will work at the show site or not. So here you can see that different switches are supporting different OpenFlow versions, and there are different capabilities. The diagram over here, this layout shows the default dlux viewer. This comes along with the OpenDaylight package. And you can see different hosts and different nodes connected together under the control of a single SDN controller. When you move to the WAN environment, the challenge here is how you see different remote islands or different domains stitched together. And then if those different islands are not stitched together, then a single SDN controller will not be able basically to create end-to-end paths. It will not be able to push the flows across the whole topology, across the whole network. So there comes the OpenFlow Discovery Protocol with a different kind of LLDP MAC address, and that helps basically in bridging, joining different islands together. And now you can see that there are three different islands, one with a blue, red, and the other one on the right side, connected through NSI, and the other through crossing two different switches, and those switches are not displayed in the middle. So in the previous slide, we saw the OpenDaylight dlux topology, but here I'm showing you a software that we developed last year for the Supercomputing conference. This is an improved version of the earlier topology. What it does is it gives you an engineering environment where now you have different nodes, different hosts, and the flow information, all from these attached units on a single web page. And then you can take this information and start developing intelligent applications based on this information, and imagine what you can do. So here I'm showing you the same three islands over here, the blue or this blue color icon where we have the node link. There's a remote side, and then there are two main rings basically, which are comprising a total of 3 islands. So in the bottom, you can see that there are different flow table graphs, and if you click on any of the nodes, you'll see its details. If you click on the host, you'll see the details of the host. And eventually, the idea of developing and working on all these software pieces is how we can install the flows and do this traffic engineering. So we developed this ring and then connected the remote sides. And then we thought that how this intent-based environment can work. So the intent for an application could be a bandwidth, it could be a shortest path, and those two can be merged together, and those can work along with other options or the other metrics coming from the DTN node itself. Because imagine there are a bunch of grid FTP servers on one side and a bunch of grid FTP servers on the other end side among these two tier 2 centers, but those have different capabilities. For example, some of the DTNs are just 10 gigs, some are 40 gigs, some are 100 gig. But how do you know? So you create a common profile, generate a profile through some JSON information, and then give this JSON information to your application, and your application now have more intelligence, not just the shortest path or the biggest pipe, but now you can tune your applications to use those specific DTN nodes and then do the transfer. So this is the network layout that finally we used at SC. The green boxes are all OpenFlow controlled switches. These are the Dell Z9100 switches. The blue ones are the switches which were not under the OpenFlow, but mainly the ring was controlled through the SDN. And then there's like WAN paths and a couple side demonstrations, including Mellanox using the parallel PSM optics for the 100 gig, and yeah. So using these compact form factor 1U switches coming up by Dell and Inventec and other hardware vendors, it has really reduced the footprint rack. Now the same racks can host many 100 gig ports, and those ports those ports at the same time can be used either as 10 gig, 40 gig, 25, 50, or the 100 gig. So using those new silicons and those new chipsets in these 100 gig switches, which are coupled together with the OpenFlow, one can really scale down the whole footprint and the energy usage of the whole environment. So you have seen the graph in the past slide, but in this is the live topology that we captured at the SC. So we have the ring, and we have different hosts connected to different nodes, and the traffic that we captured that moved across this whole ring was close to around 500 gig on one. No, I think it's 750 gig full duplex crossing the whole ring. So there was more traffic, but because of the OpenFlow stat bugs, we were not able to capture the whole all the ports which were involved. But in addition, there were some challenges in how one can connect the WAN side. We had some issues for the 100 gig link going across the southern route to reach the Stanford University, because Stanford booth was connected through our Caltech ring. So finally, on the last day, we were able to push across 70 gig coming from the Stanford booth, landing on our SDN ring, crossing that SDN ring, and then going out over to the WAN path, and then going all the way through Cenic and landing in the Stanford campus. So because at the efforts of this whole conference, we finally were able to release this software on the GitHub. It is available there. Anyone can download and use it. There is a README file which is available, and it's really easy to deploy. It has visualization power. It has a Polar daemon which collects all those data records, and it collects. It has Python libraries in the backend. So it's a small package. It's not a big package, but it really helps the developers or the application engineers to work on more intelligent applications. So some of the activities regarding the OpenFlow, which we took on, starting from the OLEMS project, starting in 2013, and so we used the Floodlight controller initially, and that controller was basically a precursor to the OpenDaylight consortium. So then we moved on and migrated the OLEMS controller to OpenDaylight. We rewrote all the algorithms, and the algorithms which were involved are the shortest path and the maximum bandwidth availability, coupled with others. Our future plan is to use the application layer traffic optimization algorithms and the modules which are now designed by Dr. Richard Yang at the Yale University, and we'll integrate this OpenFlow next generation software that we developed at SC with the ALTO. This is a short primer on the OpenDaylight controller. There are different components. We don't need to go deep into that, but there's a netcom, there are Yang models, MD cell and AD cell, different pieces of the OpenFlow, of the OpenDaylight controller. We have heard about NorthBound. We have talked about SouthBound, so what they are. So NorthBound is basically when you have an application talking with your controller, and your controller takes that input for design its own, convert it into its own format, and push it down to the switches. And those information which you are pushing down to the switches could be a flow, a change of flow, or for example, traffic rate limiting, or putting DSCP values for certain traffic. So this is what I talked about, the ALTO integration with our OpenFlow next generation software. So there are different components available in the ALTO. One is, which is interesting, is the SPCE, the Simple Path Computation Engine. It can take different metrics coming from the network or from the DTNs and can take better control of the whole environment. So in the past, not using the OpenFlow protocol, but using the OSCARs and NSI and the OESS, we did some other prototyping for the CMS applications. So there are a couple of applications which are involved in the CMS. These are FTW, XRD, ESO, and the FTW was the one which we are discussing here. So we modified some of the components of the FTW that, okay, in a regular environment, we have a few machines talking to each other on a regular IP network. How we can give the same application a different environment, a different dedicated path controlled through the OSCARs, and using the FTT application. And as you see that once that environment is given to the application, the TCP ramped up and it reached to 10 gig very easily. This is a demonstration that we did at FIU for the Internet Focused Technical Workshop. There we demonstrated the similar capabilities. As I talked earlier, that the SDN and many other features, they are not like in an infancy mode. These are now, you can say that these are well developed now, and one can really take benefit of those and integrate them into any application. So this was a demonstration of doing such thing, where we took one application, integrated the OSCARs, integrated FTT, integrated NSI, and different other things, and then we brought it all together. And here you see 4 different end sites all connected together through these software pieces. So over here you can see that Caltech is connected to the RMP in Sao Paulo in Brazil. Caltech is connected with Michigan. Michigan is connected with the AMLite. And this was all monitored through the Mona Lisa agents installed on the end sites. Moving forward, OVS, Open Virtual Switch. This is another very interesting piece of software which is available on general Linux distributions. You don't need to compile it specifically for your own distribution. The idea of showing this slide over here is that so the 100 gig backbone, for example, within Cenic or within ESNet or Internet 2, it's a shared resource. For that shared resource, there is a desire that the end host should not overwhelm that backbone, which is getting shared by the other people as well. So how we can enforce this policy at the end host? So as I discussed earlier, that now we can take the metrics from the DTN host directly and then can influence what we want to do with those DTNs. For example, if there's a 100 gig backbone from here to Sunnyvale, and if you don't want to overwhelm, even by knowing that the 40 gig systems can really drive at 40 gig, you want those 40 gig to drive at 20 gig. So using these different policies, now OVS can be signaled, and it can drop down the traffic, or it can meter the traffic, put some DSCP values if desired, to different levels. So next round of developments, we are working with ESNet and other partners on the Sense and SDN Engineer. These are 2 different projects, and the idea is to have a common infrastructure available for various applications, rather than having one application designed by one researcher and another, for example, piece designed by another group, and then both of them are not talking with each other. So the idea is to create a centralized CNOS environment where different applications can talk with each other, and that CNOS basically can provision the path for you wherever that is deployed. This is the final end-site orchestration which we are looking forward to be developed. You see that there is like a WAN SDN orchestration. This is the CNOS software. And then the application, the high-level services like ESO, it can take benefit of this CNOS and the OVS on the end sides. They can flow, they can steer the flows starting from the end sides. So I thought it might be interesting for the PRP over here and other discussions how one can design DTNs which can really exploit the PRP backbones. There are different choices and opinions when you want to design such a system. For example, if you are constrained in the rack space, then how many 1Us do you need? Whether do you need like a single socket or a dual socket, meaning that one NIC cannot be handled by a single socket, or you definitely need 2 sockets for that. You want to have a white box, or you want to use a traditional vendor like Dell, HP, or any other. How many PCI slots are needed, for example? Do you want to separate the I/O and the network on each of the motherboard slot, or do you want to combine them together to have lowest latency coming from a single processor and same cores on the processor? Onboard cards versus the add-on cards, and other features like BIOS tweaking, which are available, for example, in the SuperMicro motherboards. So, as I discussed earlier about the SC15 conference, we had to, just like the SDN test lab, we had to deploy this 100 gig environment so that we know that what are the capabilities of these 100 gig NICs and whether they can really be useful at the WAN or at the LAN or in the ring, or how many cores you need for a 100 gig NIC, or what are the capabilities. So this is the initial design that we used at Caltech, and these are the Haswell systems with Mellanox VPI NICs, and we also use the QLogic NICs. So using the Haswell system and the configuration on the last slide, and after doing lots of tuning, a single TCP stream, we were able to go to 68 gig. And this is pretty consistent across this plot. We didn't use the iPerf or iPerf3 or any other software, which is a network testing software. Rather, we used an application that is used to transport large data sets called as FTT, and it is also an open source software designed by one of our team member here at Caltech, and it is available through the website supercomputing.caltech.edu. With further fine-tuning, we can see that using 2 TCP streams, we can go in parallel at around like 94, 95 gigabit per second, and using the minimum number of just 4 cores in together. So not just the network or the network cards, you also need to have like a proper I/O subsystem if you really want to design a DTN, which is taking the network traffic in and now writing on the disk drives. So we need to consider which file system we need, for example, XFS, BTRFS, Ceph for distributed file system for the storage, and another challenge is that sometimes we do this FIO testing on the disks, but then it boils down to that how we can mount all those drives or all those devices on a common mount point so that the applications can use all those devices together and take the full capacity of those devices rather than writing on them individually. So there are a couple of options which are available, and lots of tuning is needed. It's not just like you just do a yum install and the ZFS is there to start working for you. So MDADM, the old school software is still there, ZFS, and then of course the traditional hardware rate controllers are there. So I thought that this slide might be interesting just to throw out in a sense that what you need for a 10 gig network, what you need for a 40 gig, 80 gig, or 100 gig network, what kind of drives do you need? So the top one is a Samsung M2 drive. It can do 13 gigabit per second, so a single drive is good enough for a 10 gig NIC. For a 40 gig, you need 3 Intel drives, which can write at 43.2 gigabit per second. And for 100 gig, you need 4 of those new Intel drives. I'll show you on the next slide. The drives I mentioned in the previous slide, they're all NVMe. They're not standard SATA or the AHCI-based drives. These are the NVMe drives, and the advantage is that they are bypassing all those complex and costly layers which are taking lots of CPU cycles. So these NVMe drives, definitely they are costly. They are more compared to the standard drives, standard SATA drives. For example, $2 per gigabyte is their kind of base price, while for standard SATA drives, it goes from 24 to 40 cents. But if you are doing like HPC or designing a burst cache system design, then you need to go for the NVMe. SATA will not help even aggregating a large number of drives. So these are a couple of drives. For example, the drives from Mangstor, they are very consistent, 2.4 gigabyte per second throughput per drive. It's a dedicated FPGA controller. Intel came out with new drives called as DCP 3608, and I'll show the results in the upcoming slides. They can write at 2.8 gigabyte per second. The old DCP 3700, it's a smaller PCI slot, X4 width. So X4 width meaning the less number of PCI lanes, thus you cannot move faster data. Even the drive is capable of doing that. And using the M2 PCI cards from Samsung, there's a small adapter. You can put those M2s together on a single adapter and can take benefit of having two M2s on a single PCI slot. So we also need to look at that if you are bundling together a lot of NVMe drives, then whether the same motherboard or the same PCI structure will remain there, or you need a different set of chipsets now. NVMe drives are connected directly to the PCIe bus. Basically, there is no other controller which is after the processor connecting those traditionally SATA drives. So now you have NVMe, PCI bus, ribbon cable going straight to the processor. So there are two servers which I use in my experiments, one from CRSI and the other is from SuperMicro. The diagram on the right side is shown from the two CRSI. There you can see that a single CPU is giving out a single X16 PCI Gen 3 bus, which is expanded through a PCIe expander into 48 lanes. There are 12 drives. One drive is taking 4 lanes of the PCI. So we don't have that many PCI lanes in a single processor. A single processor these days is able to provide you 40 lanes. And the upcoming in the next year we'll see that they are going to 48 lanes. So so in order to have all these NVMEs connected together, we really need to have either more PCI or an expander or a switch chipset. So in some of the tests we did was we saw that just 7 drives are good enough to fully utilize a PCIe X16 bus, and the other drives are there to store the data to be aggregated in a common pool. But in the previous slide, as I said, that there's a single PCIe X16 coming out from a single processor in this design. There can be more X16s coming to another expander chipset, PLX, but that will be another design for having such a machine. So 7 drives can easily outpace this PCI Gen at 191 gigabit per second altogether. Then of course there are different overheads coming from the application or from the processor inside. This is a benchmark using the Intel NVMe drives. So this is a benchmark on the raw drives. There are 5 drives in the system, but each drive is exporting itself as 2 block devices. So there are 10 block devices which are available to the OS. The CPU, so the important thing is here is that these 5 drives in aggregate can do 112 gigabit per second, and this is good enough to drive a 100 gig NIC. And the good thing is that these NVMe drives are fast enough that 93% of the CPU is just idle, and only 6% is used by the other applications. So now it's time to aggregate all those drives together using an Intel container, and on top of that, using a file system called as XFS. So we can see that still we have the 112 gigabit per second, and the CPU utilization went a little bit lower to 84%, which is still available. Another test ran on the Mangstor NVMe drives. So this is a raw test. The CPU utilization is, which is available for other processing, is still at 86%. So these drives can write at 2.4 gigabyte per second per drive, and I think there's enough capacity available within the processor to drive at least one more 100 gig NIC. And the challenge here, how we can add more drives, is the problem of having more slots on the motherboard. There are limited number of slots. There are limited number of PCI buses. And you have to live with sometime with the combinations which a motherboard vendor is providing to you. The most convenient motherboard vendor is the SuperMicro, which is providing you various X8, X4, X16 slots, a different combination. So now you have the NVMe drives. Whether are you using them properly or not? So I didn't look properly on these when I was testing these drives initially. So I saw that why the drives are throttling down, and you can see that there are 4 drives which throttle down to a level that they had to preserve themselves from burning out. So the idea is that all these drives, basically they have FPGAs which are doing lots of computation by spraying those bits across different RAM chips across the whole board. So they try to preserve themselves by not burning out. So once you have good airflow, they really take you back to what they can do. These are the different 100 gig switches that we used at SC and still using them. There are different features available from each of the vendor. For example, either there's a Linux available in Inventec switch, or ONI-based environment where you can load like Cumulus or any other Linux, or Pika OS, for example, on any of these switches. So all these switches, they support ONI right now. And Inventec is using Pika OS. Mellanox is working with Cumulus Linux. So still now, there's lots of confusion on, because this technology is still in infancy. And there are different pieces you need to know well in advance about the optics, about the link auto negotiation, and whether some of the NICs or the switches are supporting FEC or not. So QLogic is, for example, is not supporting auto negotiation, neither it supports FEC. But the good thing is that the link comes up very quickly when you connect it with the switch, because it's hard-coded at 100 gig, and there's no FEC. So as soon as you connect the cable, the port is up. But what we have seen with Mellanox is that it supports auto negotiation, it does support FEC, and even if you have like ports properly configured, it takes like sometime 5 minutes, sometime 10 minutes, sometime it never comes up. Moving forward, so we have been listening about the 200 gig network and the 400 gig network, and I thought that maybe it's interesting that what we have to look around for this next gen networks. So currently the PCI Gen 3.0, it supports only 8 gigatransfers per lane. That makes, like, for an X16, you can reach to 128 gigabit per second, full duplex. It's a full duplex serial bus. PCI Gen 4.0, it can go, the X16 can go to 256 gigabit per second, and X32 can go to 512. So you really need a processor like Skylake, which will be available in 2017 to have more PCI lanes, and also an X32 bus, Gen 4, which can, and if there's a NIC available for 400 gig, then such kind of buses or slots are needed. And of course, this is not just limited to the bus, because the data has to go back and forth among the memory and the processor, and then you need faster clock rate among the memory bus as well. So I did 2 tests. I don't have the one with the TCP, but I did this test with InfiniBand using the Mellanox OFAD distribution. There are 4 streams together. In this diagram, there are 2 NICs on one processor, 2 NICs on the second processor. So there are 2 NUMA nodes, NUMA 0 and NUMA 1. So if we run this IB test on 2 of the NICs, then we see that there's like 97 gig per second stream each NIC which is handling, and in aggregate it is about like 200 gig going across a single processor, coming straight from the NIC memory to the user space, bypassing the kernel all in all. But when we use the same thing with the TCP or going across the kernel, we see that the aggregate throughput on a single processor goes about, with the jumbo frame of size 9K, it stays at 110 gigabit per second. And if we reduce the frame size of Ethernet, which are on the same processor, down to about 2,000 to 1,500 bytes, the performance goes higher, close to like 160 gigabit per second. So we are still investigating where is the problem, whether it's the application, whether it's the processor, whether it's the driver, the NIC, or a combination of all these together. But at least if there's an application which can take benefit, just like we have seen in the past, RFTP, RDMA-based FTP, written by Stony Brook, a group in the Stony Brook, then if we let that application use this network, then they can exploit this network with just 4 cores used out of these 28 cores, or how many cores there are in the whole box, and let the remaining cores to be available for the applications. And these all streams are very consistent. You can see there's no big deep spikes. So special thanks to our research and the industry partners who have been helping us a lot in providing these all these great switches and the software pieces, and to our research partners as well. So thank you very much. If you have any questions, let me know. Okay, thank you.